Our second topic, we'll talk about RF simulation prepared by Khaled. He is the signal integrity design engineer with Smith Interconnect. He has 25 years of experience in semiconductor front and back-end testing process, include PCB design, high-speed device contactor, and HFSS signal integrity simulation. Okay. Let's go for the presentation of simulation.
Thanks, Kenny. Thanks for this nice introduction. Good evening, good morning, everybody. Good evening. I'd like to start by thanking my colleague, Kevin DeFord, who's now the Senior Development Manager of Technology, and Robert Friedt. He used to be RF test engineer, and now he become test engineer manager, test lab manager. So today I will be talking about RF simulation technique. And this is a very straightforward simulation presentation and very simple. I will show the standard technique for the simulation and what the industry standard for that simulation and what is the gap and why we need to change. Also, I will highlight the challenge of why we need accurate simulation, and we need to show the importance of simulation and measurement correlation. Finally, I will also, in my presentation, with some summary and test result of high-speed test socket. So what is the standard for RF simulation of this socket? Most of the industry really are using simple test block or simple socket, 9 probe or 12 probe, where A stands for the ground probe around the signal, and usually 8A for single-ended or 10A for differential. And they will manufacture this socket, and they will do a simulation, and they also will do a measurement to see if they can make a correlation between the measurement and the simulation. And this will be very sufficient for many of the probe technology when we have this socket simulation like that. However, this standard simulation is not good enough, since we know that when we design a probe head or a socket or a probe, we target impedance, certain impedance, and we know that when we design a socket to match this impedance is very important, but it's not good enough. What we need to do, we need to match the impedance through the entire system, the test board and the device board, including the socket. So the simulation need to be capture the probe technology design, material, the property of the material, and also design the PCB on the bottom surface, and also the device simulation, the device simulator with the solder ball. The first, they will do the simulation, and then they will do the actual measurement on the VNA. Then we'll try to obtain some correlation to see if the simulation is correct. So next slide will be showing a very standard report that this socket supplier presented to their customer, usually insertion loss and return loss in terms of dB, and some crosstalk, and also like a TTR plot to show the impedance of the socket or the probe. So as you can see, this standard simulation methodology, it has a gap. Doing the socket alone, just 10 probes only, 8A or 10A like that, it should be not representing the customer pin map, not representing the actual test environment where you have adding the solder ball or the test board and the PCB test board top surface at least. So for creating this gap, then the result of the simulation will be only good enough for the socket only, but not enough to capture the interface between the socket to the test board or to the device board. So the need to change, we need to add to the simulation for critical high-speed signal of certain device. We need to capture the interface of the test board and also the device board, at least showing the solder ball interface with the probe and the pad or the solder mask around the solder ball. And on the bottom, we need to capture also the top surface PCB detail and the pad diameter and solder mask to the simulation to get an accurate, reliable result correlate to customer device pin map. So next will be what will be the challenge for getting accurate simulation. The challenge is most of the time the PCB design detail is not available during socket initial simulation. And what we should do is that at that time, we should start with a standard PCB fabrication design. And we also start with solder ball and just a device pad to include that to the simulation. And then at the later time, we can get the actual detail of the design of the test board from the customer and include that to the simulation for before final release. So that's the one challenge. The second challenge is the fabrication limitation. Sometimes the fabrication limitation have a wider tolerance range of the solder mask opening and the pad diameter, gold thickness, and all of that. Those can cause some degradation to the signal integrity performance, and we need to capture that. Also, the big challenge is sometimes that the design detail by itself, like the dog bone with large offset via, this is a very trouble design when you have a board like that, because now you have almost like you have two pads. The spring probe interface with one pad, and then the other pad will be sitting on top of underneath the socket material or the probe head. So when we see a problem like that, the top surface PCB have some exposed via, exposed traces, microstrip traces, solder mask. We need to capture all of this in the simulation, or we need at least to advise the customer by making some changes or recommendation, moving some traces away of our socket or probe head hardware, and make sure that we optimize all the footprint for this particular test board. And also we need to capture the solder ball penetration to the spring probe in a test condition. So this is also critical because you will have different probe height, different probe penetration inside the solder ball. This also can have a good simulation result. Because of all of that, what we did an extensive study in the next slide to see the impact of a design, PCB design like that when we have it, when we interface that with a socket, this socket or the probe head. So next slide will show what we did. We modeled two-layer PCB board with microstrip trace and with reference ground on the second layer on the bottom with FR4 material, and try to optimize this design to get a perfect 50 ohm impedance plus or minus 1 ohm with using the transit circuit analysis. And once we established that, then we added the probe head or the socket on top of this model circuit board. And then we want to see what will be the impact when the socket are making contact to the microstrip trace or any exposed metal or exposed via on the PCB. So we run a lot of analysis by using different material on the socket or the probe head, different aluminum, stainless steel, dowel pin, nylon screw, different material of the plastic, ceramic, Vespal, And we use this model to get the optimum performance of what would be the best gap of the, we recommend our footprint for the customer to avoid any signal integrity degradation from having the PCB, having the socket or the probe head sitting on top of the microstrip traces or some power via. And as you can see here from this slide, when we analyze the TTR, this is where the 50 ohm microstrip trace in perfect exposed in air, and then it will have some impedance discontinuity or mismatch when you have the stainless steel above the microstrip trace, and then dowel pin, it's actually recessed a little bit more inside the probe head, so the dowel pin does not have effect on the microstrip trace because it's a little bit further away. And then we have an Allen screw that almost close to the stainless steel level that also have an impact of the microstrip trace. And then when we have the material, ceramic or the Vespal is sitting on top of the PCB, sitting on top of this little microstrip trace or the signal pad or trace, then you will have about 4 ohm mismatch of impedance because the material. So definitely you can change the dielectric of this material to get less effect and to make sure that you try to minimize the impedance mismatch at least as possible. Make it like plus or minus 3 ohm as the best as you can. So while we did with this extensive study, we obtained what would be the optimum gap in between stainless steel, between plastic, between different material of plastic above the PCB. Now let's talk about simulation versus measurement correlation. Um, um, we have many this equipment in our lab to do the measurement for the signal integrity. We have the 4-port network analyzer. We have also gigatest fixture that allow us to do the probing, direct probing from top to bottom, or doing with the fixture, with the universal bottom PCB, device PCB, and then we have SMA and cable. So we can so we can do 100% measurement on 8A socket or 10A socket with the universal board fixture, or we can use the actual gigatest fixture to do the probing from top to bottom or top in the device on the solder ball or on the spring probe. So once we have the simulation done first on a test block, then we do the measurement. Then we use the software to de-embed the fixture or the cable and the connector, and then we will come up with a result that correlate between the simulation to the measurement. And we can present this S parameter to show the insertion loss, return loss, and loop inductance and the crosstalk as far as the measurement. And then we can compare that to the simulation and to see the correlation between them. So next slide will show the correlation between the simulation and the measurement. The red dotted line is the measurement, or the blue dotted line is the simulation, and the solid red line and the solid blue line is the measurement. So we have insertion loss and return loss correlation, and we have also impedance correlation. So you can see from these two slides, we obtain good correlation, not 100% good correlation, but we obtain good starting point correlation, because this was done by the same test engineer who's doing the simulation on a test block based on the socket design and the property of the socket, and then the measurement, and then de-embedding the fixture to get the socket alone. So the mismatch that you can see here, it's coming from some different parameter in the design to the actual manufacturing socket, some change on the electric property, some change on the skin effect of making a good contact to the solder ball using the gigatest fixture. So all this can make some little variation between the measurement and the simulation, And you're doing that by optimizing the impedance curve, and then you find the electric constant property of the material, and then you feedback those to the simulation. You will obtain more accurate result to the simulation. Then you give this optimization simulation parameter back to the signal integrity test engineer in the manufacturing side, so he can release that proof technology specification or data sheet by making another simulation using this parameter, but an actual customer pin map device. So this is the method of doing this correlation versus measurement. So now I want to show you our new enhanced methodology for the simulation. We start with designing in a simulation. We start with obtaining the customer PCB, top surface interface detail, pad diameter, solder mask, and via of the ground return. And then we also add the solder ball, the pad, and the device board. And then having these two by themselves, getting the TTR plot, make sure that is within the 50 ohm impedance or within the customer target impedance, plus or minus 1 ohm or 2 ohm at the most. And then we add to this model, we add the socket simulation to this model. And then by adding this socket simulation to this model, now we know that the board already meeting the customer target impedance. Adding the socket into the model, we now can characterize the socket itself and make sure that we fine tune the socket design parameter or the socket simulation parameter to obtain good result and also to minimize the deviation on impedance. By doing this, now we know for sure that the socket simulation is very close to customer test setup or test environment, because we're using the detail of the design of his test board and also his device. So this is the new enhanced method for doing a simulation for high-speed test socket, only for critical high-speed signal, high-speed technology. The next few slides will be just an example of a test result of one of our latest high-speed test socket, DaVinci 56 gigabit per second, showing the return loss and insertion loss using this new latest enhanced simulation technology by adding the device board and adding the test board and getting the result, modifying the parameter of the simulation to get the best performance of the result. And this is a crosstalk of the differential. And this is a TTR of the terminal and differential. So in summary, I like to close by saying that signal integrity simulation is very critical component and to designing a high-speed test socket. Extensive simulation are often required during socket development that can reduce the risk of making design error and reduce the overall development time. And also by including the package board, RF pin map, and test board to the simulation, will guarantee or will generate more accurate and reliable simulation result that come very close to customer in use test environment or test final test. I think I finished a little bit early, it's 20 minutes, so we can go back to any of the slides if we have any question.
Thanks, Khaled, for the great presentation. Okay, so we have two questions from our audience. Okay, the first one is from Yang Shen. What is the waveform of the excitation signal of the time domain reflectance?
Can you repeat the question again? What is that?
Yeah.
Rise
What is
time?
the, sorry?
What is the rise time?
Yeah, let me repeat the question. What is the waveform of the excitation signal of the time domain reflectance?
Okay. So these here usually we ask the customer what is the time rise for his test measurement or test setup. We are putting 25 picosecond as a rise time, and this is a good starting point. We have some design we did 15 and some design 35. So 25 picosecond rise time for the time domain reflection. This is our setup.
Okay. The second question is from Ideal. He asked, do we need to consider anodized layer, if any, on circuit material during simulation?
To consider what?
To consider the anodized layer.
Anodized layer.
Like the plating.
Yeah. The for IM socket, for coaxial or impedance control socket, the anodizing, it's a proprietary to supplier. We have a proprietary property that we use for not really just anodizing, it's a coating. It's a high speed coating and high temperature coating that has a good property for signal integrity. So these are proprietary information from supplier for supplier.
Okay. Okay, so the third question from Noel Gu. The simulations and actual measurements as the PCB and circuit. How about other hardwares such as test handlers, handler change keys, IC workplace circuit alignment plates?
Yeah, those would be too far away to have impact on the simulation. I'm very sure you could have impact on simulation, some even some temperature and some light in this floor. Some many things can really have impact on simulation, but these are uh, far away from the interface between the device to the socket to the board. What we are trying to capture is usually we capture um, the critical component that make contact to the piece to the socket from the device to the test board. We don't add cables. We don't add a semiconductor. We don't add other like we don't add layers like layer 3 and 4 and 5. We just add the reference layer of the ground, which is the second layer, the material of the first layer, high speed or the FR4, and the same thing for the device. Anything beyond that, that might be specific, and it might require specific simulation, which we did. We have simulation, like I think I have a small picture here showing showing this board here, like it has like 10 layer. So yeah, we could put a whole Lego board, 10 layer board from the bottom, and on the top we could also put like 4 layer of the device. But that's only specific simulation per request, and you will
Okay,
have less impact on the signal integrity performance of the socket in particular with the interface of the test board and the device board.
okay. Okay, the next question is from Kumar. He has two questions. The first is, will you do SI after low board design with particular material, stack up BGA pad? The next is, how will you decide rise time of TDR, the stump rule?
Yeah, I answered the question about the TTR rise time. Usually our standard is 25 picosecond. Sometime we'll go faster, 15. Sometime we'll go slower to 35 based on the customer setup. That's for the rise time. And for the first question, he's saying that how do you define the PCB material? Yeah, so usually we ask the customer what is the first layer, the high-speed layer, what the material that been using. We have database for the Raja and for any Panasonic or any material of the PCB. Or if we don't have this information at front, we'll use FR4, and later on we'll fine tune the simulation result based on actual material. And usually the PCB material can change impedance in term of like half ohm to 1 ohm between material to another material. So it's not going to show It's not going to be very big different, but it will be improving the result by knowing exactly what the material is being used in the board.
Okay. Our next question is from two audience. I think it's all about the crosstalk. Okay, so how do you consider the crosstalk performance if by including solder ball or without solder ball, and how to improve the crosstalk performance of socket?
Well, crosstalk is a very big challenge, but here is showing the picture again. We definitely have to, for the crosstalk, we definitely have to use the solder ball, and we have to shield the solder ball with shielding the IM material of the high-speed test socket. When you shield the ball with the IM material, you will get the lowest return loss, the lowest crosstalk, and the best performance of the crosstalk by shielding the ball to the top, to the maybe 90% of the solder ball. And the other than that, the crosstalk is pattern dependent, so it's based on the customer pin map, and usually the differential crosstalk is more recommended to be surrounded by ground, 8A or 10A at the least. If you have a differential pair with lack of ground to shield the signal, then you will have some high crosstalk. So the customer need to make sure the design of the device and the PCB is good design for differential. And for us as a circuit supplier, we need to include the solder ball to the simulation, and we need to recommend as much as possible to shield the solder ball with IM material.
Okay. Okay, I think the last question is the excitation signal a step waveform or an impulse waveform?
In what?
Is the excitation signal a step waveform or an impulse waveform?
In power form.
Impulse.
Impulse, yes.
Yeah. Can you answer it?
So the last key to everybody or to the audience is that please, you need to continue to include in your simulation as much as possible device characterization and PCB characterization into the model. You need to have more skill about adding the PCB to the socket simulation, but it's a key. It's a key to match the impedance of the entire system as an entire test cell, which is a device, socket, and a PCB. That's the key note you take from this presentation, is to make sure that you can always include solder device board and test board at least.
Okay. So I think it's time. Okay, so thanks for your great presentation.
We want to thank our sponsors once again, Test Tooling Solutions Group as our premier sponsor, JDT Technology, our honored sponsor, our distinguished sponsors, Nidec SVTCL, Smiths Interconnect, TSC, and Feldman Engineering. And a reminder that you can reach out and contact them through the website, through the chat or message buttons there. So please take a moment and thank them and reach out and ask them about their products and services. I'm sure they will be very happy to help you. And also I want to thank our media partners, ACT with Silicon Semiconductor China and EE Times with an upcoming Double Summit event next month. So you can find links to this on our website. And then an extra special thank you to Test Tooling Solutions Group being our premier sponsor. Certainly a lot of innovative solutions there in this space of test equipment and test consumables. So please thank them once again. And lastly, I would like to thank all of you for participating in TestConX China. It's been a great pleasure. I'd like to thank the authors and the committee, but most importantly, thank you for joining us. We hope that you found this to be informative and useful, and certainly appreciate any feedback you may have. We look forward to seeing some of you at TestConX in May in Mesa, Arizona, and then TestConX China 2021 in the fall in Shanghai again. So thank you. Have a good rest of your day.